Okay, so good morning. Welcome to this last day of the workshop. So this morning we have a session mainly on sources. The second and third talk are on primordial sources. And the first talk is by Killian. This is a bit of a provocative talk, producing gravitational waves in the lab. So you have 12 minutes.
Okay, thank you. Can you hear me? Yes? Okay, so thank you. First of all, thank you for being here, especially the morning of the last day after the dinner. I know it's not always easy, so thanks for being here. Also, I want to thank the organizers for this wonderful week and the meeting. So in this presentation, I will discuss, yes, maybe in a provocative way, the possibility to generate laboratory-controlled gravitational waves by using twisted light. So as it has been already spoiled by John Luca on Wednesday, you will see that in the end, well, it does not work. But still, there are, I think, some elements that are interesting in this work and some things that might interest some of you. So this presentation is based on the following paper that has been done in collaboration with people from Oxford, Edouard Attengar, Amier Bouchel-Baya, and Peter Norris. So those guys are the specialists in laser physics. And we have also worked with Aurélien Barraud in France and Chun-Chan Lin from Krakow in Poland. So I want to start this presentation with the following sentence, which states that the action of gravity on light is well known, and indeed it has been extensively studied over the past decades, but the converse, and by converse I mean the way light itself acts as a source of gravity, still remains to a large extent unexplored. And it is this second path that we will try to bring new elements of answer through this study. It's okay. So light can carry orbital angular momentum, and the OAM of light is characterized by an azimuthal phase dependence of the electromagnetic field. If you look at the trajectories followed by wavefronts of such light, you will see that those trajectories are very similar to the one of two bodies that would in spiral in space. So this is why we had the idea in the first place to compute the gravitational waves that will be emitted by such systems. So there exist different types of twisted beams, such as the Laguerre-Gaussian beams or the Bessel beams, which are the beams we are interested in today.
Maybe click once on the slide.
Yeah, this is what I did. Up. Maybe I will leave the mouse here. So how can you produce Bessel modes of twisted light? Well, Bessel modes can be produced over a finite region of space by using an Axicon optics that will cross the wavefront of an incident beam towards a certain finite region of space. And the interference pattern that is produced here in the center over this conical region generates a Bessel mode of light. So in our study, what we really did consider as a source of twisted light and therefore as a source of gravitational wave is a subset of this cylinder region, of this conical region in the center under the form of this dark pink cylinder in here. So Bessel modes can be modeled as an infinite superposition of plane waves, which wave vector lie among the previous conical surface. Their OAM, their orbital angular momentum can take this form, so it depends on a certain OAM parameter, and as well as some Bessel function, hence the name of Bessel mode. So from the first expression in here, you can compute the components for the E field, and by use of the Maxwell equations, and mostly the Maxwell-Faraday law, you can compute the components for the B field. So as you can see, those expressions are already EV. But the only thing you have to keep in mind is that those expressions depend on the Bessel functions as well as on the OAM parameter. Obviously, in addition to that, those expressions also depend on different properties of the optical setup, such as the pulse frequency, the half-cone angle, or the beam waist. So once you know the expression for the E and the B field, you can compute the stress energy tensor of the system, which for radiation takes this form. So I do not write down explicitly the full form in the slides, because as you can already guess from the previous expressions of the E and B field, it is quite heavy, but the full expression still is in the paper. And once you know the form of T mu nu, you can compute, thanks to the wave equations, the associated space-time deformations. So to do this, we placed ourselves in the compact source approximation. So at this stage, We know the expressions of the E and B field in a certain frame that I can denote as the laboratory frame. Therefore, we were able to compute T mu nu and therefore the space-time deformation in this laboratory frame. So in order to rely only on the physical and radiative components of the space-time deformations, we had to project our result in the TT gauge. The metric deformations in the TT gauge look like this. The full form of h mu nu in TT gauge can be written as the sum of 4 terms. Those 4 terms are like this. They depend on some functions. Those functions are written depending on some other functions that are written like this that depend on those functions. So as you can see, the full form of h mu nu is quite heavy, but still it has been computed. The only thing to have in mind for this talk, the only thing that matters for our purpose, is that obviously you can express this h mu nu depending on all the optical parameters that enter into the setup. Therefore, by varying the values of those parameters, you will vary the h mu nu in here. So by varying the values of the optical parameter, you can have a control over the properties of the radiated space-time deformations. And we will see that it can lead to some very interesting effect, at least to my view. Let me take an example. For example, in here, I have represented the different components of h mu nu in the TT gauge, so the gravitational wave, in the z-x plane, where z lies along the optical axis. There is an interesting thing that occurs in here when these parameters, zeta L, that corresponds to the product of the pulse frequency times the interaction length divided by the speed of light. So when this guy becomes greater than 1, there is a beaming effect that occurs. Indeed, you can see on this graph that when we increase the frequency, so when we go from the purple lines toward the red lines, there is a beaming in the forward direction. And to my knowledge, at least, beaming in gravitational wave physics is something quite unusual. We can have tilted gravitational waves in a forward direction, but a real beaming effect, this is something I wasn't aware of. So this is something I find interesting. And more interestingly, this beaming effect, of course, does not occur towards any random angle. This beaming effect is directed towards a very precise angle, which is this cone angle alpha, which defines the shape of the conical region. So this is really the kind of subtle and somehow unexpected effect that appear when you deal with such forms of the stress energy tensor. So now that we have seen that subtle effects can appear, let's speak a bit about the main characteristics of the gravitational wave signal. So the frequency of the, yes, okay, thank you. The frequency of the emitted gravitational waves is twice the frequency of the pulse. And interestingly, it does not depend on the value of the OAM parameter, which was not obvious at all at first sight. So for the laser pulses, typical laser pulses, this frequency is in the optical range, so 10 to the power 14, 10 to the power 15 hertz. Maybe it would be possible to tune it a bit by considering the interaction of two beams of close frequencies, but, well, it's just an open idea and probably not that much. Now the strain. This is the plot that has been presented by Gianluca on Wednesday. So on this plot, we represent the maximal strain associated with the signal as a function to the distance to the source. So we have computed this strain for 4 different facilities. 2 of them in purple and in green are facilities that really tend to maximize the power inside the beam. And the other 2 in yellow and red are facilities that tend to maximize the energy inside the beam. So you can see that what you want to maximize in order to maximize the strain is the energy. So you recover the naive intuition that the effect scales with the energy. Okay, so far so good. Also, the dotted lines corresponds to distances to the source at which the far-field approximation, the compact source approximation cannot be trusted anymore. So you see that even considering the very best facilities that we have today, so the LNJ or the NIF facilities, and even the facilities that can arrive in the upcoming years, the future ICF, the emitted strain is 10 to the power minus 36, so at best 1 meter away from the source. This value is obviously very small, but it is what it is. And what about the power? Now, this is the last property I wanted to discuss because we have a very, very good control over the direction of emission of the power. There are some values of the parameters for which all the power is emitted along the optical axis. And there are some values of the parameter for which no power at all is emitted along the optical axis, and everything is emitted into the azimuthal plane. At the level of the power, there is still this beaming effect also towards the half-cone angle. So basically, we can emit the gravitational waves, the radiated power, in every direction. We have a perfect control over it. I also write down something in here, a comparison that I find amusing, that I find funny. If you look at the power that is radiated by the system, so if you put a detector close to the source, and if you compare this power to the power associated with the first gravitational wave event, you find that those two powers are comparable. Maybe you can go even a bit at bigger values. So of course, I do not claim at all that twisted beams of light do radiate more energies under the form of gravitational waves than a binary system of black holes, of course, because the distances to the source are extremely different. Thank you. But if you really think about the power evaluated at the detector location, so maybe you can have comparable powers. So in the end, in definitive, we have seen that light can emit gravitational wave. We have seen that such optical setup would provide a very, very good control over the different properties of the gravitational waves, such as the frequency, direction of emission, even polarization states. There are some setups for which you have one polarization state that is emitted. You have setups for which two polarization states are emitted. You can really do whatever you want, almost. We have also seen that subtle and unexpected effects do appear, such as this beaming effect, but the generated strengths are just too low. Even if we consider the already super impressive proposal presented by whether Aldo or Georgios during this week, we are orders of magnitude below that. And it is not without mentioning an issue that we have discussed this week with Diego, also with Germain, I don't know if they are here, that if you think of this in terms of emitted gravitons, because you are at super high frequencies with low strain, that at those values of the strain, at those values of the frequencies, you would not even emit a single graviton. So you really, really need to boost the power a lot so that the whole picture becomes coherent again at those frequencies. Or you need to decrease the frequencies. So except if we have possibilities to boost the signal, all those very interesting features will remain out of reach. I will just finish with a maybe no more positive note, which is that something that I really discovered with this study, as I am not at all in this field originally, I really discovered that beyond any possible application, the question of the gravitational field that is created by light is, to my view at least, in itself quite fascinating, and I think largely unexplored. There are plenty of things that remain to be understood on this topic. So, thank you.
Thanks a lot. So, questions, Juan?
Fascinating talk. Thank you very much. I didn't know about this, but a similar phenomenon might happen around active galactic nuclei, quasars, right? So you have a magnetic field which is channeling matter through the axis, and it's emitting a very powerful jet of particles and light.
Yeah.
Do you think that might give you a significant production of gravitational waves? Has that been explored?
Well,
because we are talking about orders of magnitude larger and more intense than this.
Yeah.
They are twisted.
But you would not have those.
Definitely by the magnetic field. This is what Joachim is asking. I'm thinking about particles and light. I'm not differentiating much here. Because particles also will be carried, they are relativistic.
Yeah.
They're going to produce a current which is similar to the one we have in light.
Yeah, maybe. Probably
what matters is energy.
Yeah. In any case, you're probably right, but you would not have the control that you can have over these things.
I'm not talking about control. I'm talking about estimation.
Yeah. In terms of estimation, you can find probably.
Thank you.
Yeah.
Joachim?
I was wondering about the same thing as well.
Okay.
Are there other questions? Yes, Valerie?
More of a comment, right, regarding what you said about the power, right? That you said, it's interesting that the power is larger than LIGO. I think that's just reflecting that the BBN bound when you plot in terms of strain is a slope, right? Because that's the line of constant energy. That's just,
Sure. It's
I think that this is the issue we always run into, right? If we plot things in terms of omega, right, we think that's fantastic,
I agree.
And then we hit reality.
No, I fully agree.
Okay. I don't see other questions. So thanks a lot again, Killian.
Thank you.